A television camera is positioned 4,000 feet from the base of a rocket launching pad. The angle of elevation of the camera has to change at the correct rate in order to keep the rocket in sight. Also, the mechanism for focusing the camera has to take into account the increasing distance from the camera to the rising rocket. Let's assume the rocket rises vertically and its speed is 900 feet per second when it has risen 3,000 feet. How fast is the distance from the television camera to the rocket changing at that moment? So let's begin first by drawing a picture. So our camera is right here and our rocket is right there. We are given that this is 4,000 feet and this is 3,000 feet, and the dy dt equals 900 feet per second. Since this 4,000 feet is not moving, it's staying constant, there is no change. So the dx dt equals 0. We can use Pythagorean Theorem to find this length. 4,000 squared plus 3,000 squared equals z squared. If you work that math out, z is 5,000. So this is 5,000 feet, and we are solving for dz dt. So to begin, we can start with this equation x squared, which we'll call this x, this y, and this z. X squared plus y squared equals z squared. And we'll find the derivative of this equation. We will differentiate this equation. 2x dx dt plus 2y dy dt equals 2z dz dt. We need to solve for dz dt. We can rewrite it as dz dt equals 2x dx dt plus 2y dy dt all over 2z. We can simplify this equation even more. These 2's will all cancel, so we're left with dz dt equals 1 over z times x dx dt plus y dy dt. So we have all of this information to find and solve for dz dt. So if we plug everything in, 1 over 5,000, x is 4,000 times dx dt, which is 0, plus y is 3,000 times 900, which is dy dt, and our final answer is 540 feet per second. The second part of this problem asks if the television camera is always kept aimed at the rocket, how fast is the camera's angle of elevation changing at the same moment? So if we draw the same picture, since it's at the same moment as described in the problem, we have 4,000 feet there, 3,000 feet there, 5,000 feet there. This is the rocket, the camera's down here. This is the angle, that's the angle we are focusing on and finding how that is changing. So we can So we can start off by saying we need to solve for this angle. So using our trig, tan of theta equals opposite over adjacent, which is y over x. Remember, we're calling this side y, this side x. So then theta, we take the inverse of both sides, theta equals tan inverse of y over x, and we know those. So tan inverse of 3,000 over 4,000, which will give us 0.644. I'll write that lower. 0.644 is theta. So now we need to find the change in theta. So if we take this top equation and differentiate it, we can solve for d theta dt. So the derivative of tangent is secant squared theta times d theta dt equals, and then we have to use the quotient rule on this side, low d high minus high d low all over low squared. D theta dt equals x dy dt minus y dx dt all over x squared times secant squared theta. Now we know everything that we need to plug into this equation to solve for d theta dt. D theta dt equals 4,000, which is x, times dy dt is 900, that was given in the problem, minus y is 3,000, dx dt is 0 because this is not changing, all over x is 4,000 squared times secant squared, and theta we solve for up here, 0.644. After all of that math, d theta dt equals 0.144 radians per second.